Shaatana Vallis is an ancient water channel on Mars in the Oxia-Paulus quadrangle. Oxia-Paulus has varied terrain, including ubiquitous craters, lava, chaos terrain, and water channels like Shaatana Vallis. Shaatana Vallis travels for about 1,300 kilometers across the Martian surface, around the length of Italy. It begins near Orson Welles crater in a region of chaos terrain and ends in Christ Planitia, a plain in Mars' northern equatorial region. The creation of Shaatana Vallis wasn't a long process, like a river gradually carving out a channel over millions of years. It was created about 3.5 billion of years ago in one rapid event. Scientists think that large amounts of water and ice were trapped under the Martian surface. The water was pressurized and perhaps kept in a liquid state by geothermal heat. Then something triggered a rapid release of this water, maybe a massive impact. As the water was released to the surface, the material above it collapsed, creating the jumbled chaos terrain. This would have been a catastrophic event to observe, as massive amounts of water surged across the planet's surface, rapidly carving a 1,300-kilometer channel. Shaatana Vallis was also much deeper in the past, but over 3.5 billion years, the Martian winds have deposited material into the channel's bottom. While it's not known exactly which materials filled the valley, one isolated patch of more recently deposited dark material in the channel is volcanic ash. The water channel is not the only one on Mars. There are many of them, and some of the largest ones terminate in Christ Planitia. Because of this, scientists think that Christ Planitia was once covered by an ocean in Mars' warm, watery past. Martian sand dunes are widespread active geological features, covering areas ranging from craters to polar regions. While found across the planet, large concentrations exist in high-latitude, northern polar areas. The constantly shifting sand blown by the planet's winds creates an ever-evolving desert landscape with diverse and striking dunes. Loose mounds of sand are found all over Mars, ranging in height from a few dozen feet to higher than some of Earth's tallest skyscrapers. Unlike the quartz-based sand on Earth, many Martian dunes are made of dark volcanic basalt. The dunes often appear in shapes similar to Earth's, including Barcon and linear types, but are sometimes covered in light-toned dust. Some, like those in the far north, appear blue, indicating specific mineralogy or frost. In some areas, unusual circular sand dunes have been observed, and many dunes are covered in frost, especially near the poles, creating seasonal changes in appearance. The speeds and directions of Mars' regional wind patterns, for example, could be estimated by how quickly a dune's shape changes. Because dune movements erode and expose rock formations that might host ancient habitable environments, understanding the planet's winds could help researchers identify landing sites for future exploration. This view covers the high plains about 25 kilometers south of Coprates Chasma, near the eastern end of the Vallis Marineris Canyon system. Here, the Compact Reconnaissance Imaging Spectrometer from Mars instrument on Mars Reconnaissance Orbiter has detected clay minerals, which implies substantial water-rock interactions in the past. These minerals often have a reddish to yellow appearance in high-rise images. In this observation, the minerals appear concentrated along the boundaries of polygons up to 10 meters across. Perhaps the water-rock interactions at this site were most extensive within a network of pre-existing fractures dissecting the bedrock. Rough, blue to purplish material appears to overlie the polygonal fractures in portions of the observation. We also see lighter blue to green materials. While Compact Reconnaissance Imaging Spectrometer from Mars can provide a time constraint to the compositions of these varied materials, HiRISE shows us how they relate to each other and how such a colorful scene could have been assembled over geologic time. Jezero crater, which today is a dry, wind-eroded depression on Mars, was once a calm lake, fed steadily by a small river some 3.7 billion years ago. This animation depicts water breaking through the rim of Jezero crater, depositing sediments that built up into a delta. Perseverance rover's recent exploration of the crater floor and the delta have led to scientists developing a detailed timeline for the crater's formation. They now know there were 3 major periods after water began flooding through the crater rim. First, those waters brought fine-grained sand and mud that is known for preserving fossilized life in comparable environments on Earth. Second, the crater's lake grew as wide as 35 kilometers in diameter and as deep as 30 meters, deep enough to lay down several sedimentary layers. Finally, due to a dramatic shift in climate, high-energy rivers and flash floods brought in large boulders from 40 or more miles upstream and deposited them into the lake bed, where the massive rocks lie today. This analysis is based on images of the outcropping rocks inside the crater on its western side. Satellites had previously shown that this outcrop, seen from above, resembled river deltas on Earth, where layers of sediment are deposited in the shape of a fan as the river feeds into a lake.